components providers, the autonomous vehicle stack providers. So you can see a lot of the point I'm trying to make here is that robotics is a super interesting area with a lot of like evolving opportunities, and that's what really gets me excited about this. And at the end of this presentation, if there's anything at all, I'd love for a good amount of you to be excited about jumping into this space and sort of contributing greatly in this space of self-driving. So with that, some of us might have heard over here, the different sort of levels of self-driving. So is it basically like we have a self-driving vehicle and it becomes self-driving overnight? We have a regular vehicle and it becomes self-driving overnight. It's not the case, right? So we have different levels of self-driving, and the Society of Automotive Engineers sort of defines the levels of self-driving as these, right? So level 0 is basically no automation, which means you don't even have something like cruise control. It's zero autonomy. The human driver needs to do basically everything. Level 1 autonomy is when there is a one-dimensional sort of assistance that the driver is offered, right? Like let's say cruise control, where you want the car to maintain a certain speed. You turn that on, and you're on cruise control, and you are able to automate like one level of it. Level 2, which is partial automation, is basically there's acceleration, steering managed by a computer, but the driver must remain engaged at all times and be aware of what's going on in their surroundings and stuff like that. Now, what's an example of this? An example, a good sort of feasible example of this is Tesla Autopilot, where you turn on autopilot, it keeps the lane, and it controls the acceleration in an adapted manner, but still the driver needs to maintain control at all times by staying vigilant, right? Then there's level 3 automation, which is conditional automation. So conditional automation means the driver is necessary, but they are not required to monitor the environment at all times. But they need to stay ready to take control given any scenario, right? So an example for this is, let's imagine you enter a self-driving vehicle. The vehicle is able to navigate itself and able to sort of drive itself, but still you need to be vigilant and make sure that you take control at all times. Level 4, which is like level 5 is basically a very ideal state, but level 4 is what we are sort of tending towards as we speak. So this vehicle basically should be capable of performing all driving functions under certain conditions, but the driver will have the option to control the vehicle. So it's like the vehicle drives itself, but the driver is just given an option. If the driver wants to take over, they can take over. The 5th one, which is full automation, that's level 5, is technically you take off the steering wheel, you take off the brake pedal, you take off any sort of control interfaces in the vehicle, and there is no opportunity for a driver to even be in the vehicle, right? It's a completely autonomous vehicle. So these are the 5 levels of autonomy, and until now, we've sort of struggled getting from to get from level 2 to level 3, and level 3 is pretty much where most companies are at right now, and trying to perfect that. But level 4 and level 5 is still yet to be realized in many forms, and it is going to take a few years. It's going to take it's a super hard problem, so a lot of like talented people are working on this. Despite that, it is one of the hardest problems of this decade, or if not this century, and that's why it's going to take efforts and time to achieve that. Now, going into how a level 5 self-driving vehicle concept sort of looks like, this is one concept from Bosch, where you see you don't have a driver at all, right? You just have a vehicle, and seats. Basically, that's it. This is a company called Zoox, which has revealed its fully self-driving vehicle very recently. And this is like a few of my friends work here, and this is a truly sort of designed for level 5 kind of self-driving vehicle, because there is no driver's seat over there. There's just a cabin, a couple seats. You hail it using an app, get in, and then it drives you wherever you want. So pay attention to all those sort of devices on the top right and top left corners of the vehicle, because that's what I'll be getting into soon as well. So now, thinking about like how self-driving vehicles even work, right? How do they operate? What is this thing? At a very high level, this is what happens. Okay, so it's basically like a human. There's a sensing, so we use our ears and eyes, and then there's like a perception, which is you sense certain things, and then you perceive about like, okay, so what is going to happen, right? Given a certain scenario, and then you make a decision about what you want your vehicle to do, and then you implement that decision through actuation, right? So basically, it comes in the form of let's say we look at a cyclist going down the road. We use our eyes and ears to understand that there is something going on there, and then we perceive it. Oh, there's a cyclist going down the road, and then we predict, okay, which way is this cyclist going? Will this cyclist come in our path? And depending on what it is, you make a decision about how you want to control your vehicle, and then you implement that decision by controlling your hands or controlling your foot, and giving cars the appropriate command in the form of steering or brake or whatever it is. And a self-driving car basically operates the very same way, and we need to replace the eyes with different sensing modalities that we'll go into. And also the brain with high performance computes, high integrity computes, and you need to figure out a way to inject those signals into the vehicle and actuate specific devices in the vehicle to trigger some actions. So what does this look like in real life, right? In real life, there are several different modalities of sensing, and there's a reason for all of that, which we'll go into. So there's the GPS, obviously, because the vehicle needs to know where it is at. There's a LiDAR. Then there are like video cameras that are being used. There are radars that are being used. There's a central computer that processes all the information. There's ultrasonic sensors that measure the position of the objects next to the vehicle, like let's say a footpath or something like that. And then there's the odometry sensors that keep track of how much distance the vehicle has traveled, which complement the GPS in terms of localization and locating where the vehicle is in the world. Now, how does this look like in real life, right? Like these are all, of course, drawings. How does it look like in real life? So here's something you can see where a Tesla vehicle, it's either a Model S or a Model X. This is a Model X, actually, that's driving itself. Now, what you can see on the left is nobody is controlling the steering, and the car is on autonomous driving, right? So the vehicle recognizes the speed limit and maintains the speed limit. It also recognizes the lane markings, other agents around it, other vehicles around it. And on the right, you can see what the vehicle cameras are actually perceiving, right? There's a left rearward vehicle camera that is pointing back, a medium range vehicle camera that is pointing forward, and then the right rearward vehicle camera that's on one of the repeaters. And you can see how it is perceiving the lane, how it's detecting the objects around it that it needs to avoid, or the speed signs that tell what the speed limit of the road is. So this is technically how there's a lot of details underneath it where you need to train a model, the neural nets to necessarily detect what is a vehicle, what is a pedestrian, what is a road sign, what is actually happening when you talk of street markings, what to avoid. There's a bunch of like neural nets that need to be trained with a ton of data. But overall, this is what's happening inside a Tesla. And a Tesla has very low, very less number of sort of sensing modalities. It just has cameras and radar. Whereas other vehicles have like LiDAR and other things that sort of assist the perception. This is another example of after a vehicle actually, perceives the world around it, how does it actually plan its track, plan its motion, right, for the next 5 seconds or 10 seconds. And this is how the self-driving vehicle basically thinks. Inside its compute, it is basically drawing a box around all the agents that are around it, and understanding where it is actually in the world, and drawing its own path, what path it will take for the next few minutes or seconds, and then traversing that path and watching for agents that come into that path. There's a lot of computation and math that obviously goes into this. I'm just giving you an example and showing you what happens inside it at a super high level. Feel free to ask questions later on. But yeah, this is what happens. And this, what you can see, is a LiDAR point cloud. So what a LiDAR basically is technically it is a bunch of lasers that the device shoots out to the world, and then it receives the rebound from targets, and then based on what it receives, it draws a point cloud of the world. So there's this super fast spinning sort of beams of light going out. Whatever is received, it starts perceiving the world around it based on that. And on the top left, you can see the actual camera feed of what's going on. And similarly, you can see what the radar is perceiving on that point cloud that you can see in down below. This is another example of some cool looking sort of graphics. This looks like an artist's work, but technically this is a LiDAR's perception of the world. So I believe this is like a traffic jam or something that a vehicle is in, or a busy road. So you can see pedestrians walking by. You can see a lot of vehicles stopped over there. And this is how a self-driving vehicle through LiDAR perceives the world around it. This is an example of a left-hand turn being done in autonomy. So in the bottom, you can see the cameras that are looking at the traffic light and also at the oncoming traffic. And then you can see this is actually a Waymo vehicle, and it stops, waits for the other agents to clear, and then when it is safe enough, it makes that turn. And all these bounding boxes are other agents that it detects. And you can see, it has already planned its path. It has also it also looks at pedestrians. So this is basically how this perception stack looks from the inside. How does it look in reality? So different companies design it in different ways. Again, it depends on the mechanical engineers and the industrial designers that design the sensor pod and all the sensor distribution. In a Tesla, you can literally not see like any cameras when you just look at the car, right? Like you can see just a very sleek, plain design. But in many other vehicles, you can see LiDARs like this, cameras, those little like objects around that ring that are pointing out, they are all cameras. You can also see like these flat surfaces between the cameras. Behind that, there is very likely a radar as well. Plus you'll also have to think about things like how do we make this watertight? How do we seal this? And like there's a lot of like ingress protection that this needs. A lot of mechanical engineering aspects there as well. Of course, electrical engineering aspects here. There's other problems that people deal with also, right? Like what if there's dust on the cameras? How do you clean that? When there's a self-driving vehicle, that needs to be able to operate either with limited number of cameras, some number of cameras taken out, because of dust or whatever it is, or it has to be able to like clean itself, where if you look up on the internet, you can see little wipers on a Waymo vehicle cleaning the cameras and cleaning the LiDAR pod and stuff like that, which is super cool and exciting. So moving on to how it looks like, what sensors are primarily used for what? Now they serve like multi-dimensional sort of use cases, but in general, the ultrasound sensors are used only for park assist because they are, they have a very low range, limited to probably a few feet or a few meters around the vehicle. There's short and medium range radar, which is typically used for like blind spot detection, collision warning, and cross traffic alerts and things like that. Then there's the LiDAR, which is used for a more of a emergency braking and pedestrian detection in a longer range. And then there's the cameras, which offer a surround view, rear view. It also, there's like narrow field of view and wide field of view cameras that, accordingly detect, either traffic lights or oncoming traffic or distant traffic, stuff like that. And then there's a long range radar that helps in adaptive cruise control. So adaptive cruise control is where, you are closely following a vehicle and you want to maintain a certain distance. And when the vehicle in front of you or any object in front of you decelerates, you need to decelerate along with it automatically. And that's what the long range radar serves the purpose of. Again, these are all like I mentioned these applications in general, but they are used to a certain extent cross-functionally as well. But now we might all have the question, what is preventing us from loading these vehicles from a hell ton of like vehicle sensors, right? Why can't we just go redundant on everything and put all the sensors in? This is the reason why. There are some sensors are good at certain things, and some sensors are, they complement each other when it comes to capability and what they are good at. So the green check marks that you can see here are favorable aspects of that particular sensor, right? And then the red check marks are unfavorable aspects. The yellow check marks are like, like it just cuts the border there. As far as cost is concerned, camera costs the least. Of course, it was not the case a few years ago or like a decade ago or something, where cameras were actually expensive. Now, camera technology has really smoothened out because camera is widespread in application, right? You have a camera in your cell phone, and it used to take the amount of cameras at one point in time used to cost multiples of a cell phone, and now you have it within your cell phone with a really good resolution. So cameras are pretty cheap now. LiDAR is still the most expensive sensing element on the vehicle. That is why Elon Musk is a big proponent of not using LiDARs on vehicles. So a Tesla vehicle does not have a LiDAR, primarily because they are very, very unreliable. So you can see that reliability is very low. They are expensive. And when you're building a mass market car that you want to put in the hands of like so many people, you cannot have one device over there costing half the amount of the vehicle, right? That is also unreliable, by the way, and you need to probably keep fixing that every few very frequently. So that's the main rationale behind not using a LiDAR on Tesla vehicles. And Tesla has a very sort of strong stance on that, which is made like publicly known as well. In general, yeah, you can see the other things like illumination. Camera doesn't do good under illuminated environments. But then if there is no light or if it's nighttime, LiDAR does good because it is literally shooting the light waves out, the lasers out. Radar does good as well. So, it gives the vehicle some sort of like superhuman capabilities there. Noise, again, LiDAR is susceptible to a lot of noise. If it's raining, it doesn't work that well because the droplets reflect the light back. radar doesn't do well, but camera does pretty well. The noise circumstances in camera are relatively less. Whether camera does okay, and so on. Basically, you can see how they all complement each other when it comes to uh, their capabilities. Now I'm going to show you an example of how a vehicle reacted when there was a bicyclist cutting into its lane under full autonomy. Again, this video is also from Waymo, and you can see on the bottom left where unexpectedly there was a bicyclist that cut into the vehicle's lane, right? So now what is the vehicle actually doing here, right? So on the right, on the main image, you can see that the vehicle has already planned its path, which is the green path, and it is detecting that little sort of trailer on the right, and it also knows that there are bicyclists on the right, and the red line that you're seeing is the car predicting the path of the bicyclists. And how does it predict it? It basically, there's an object in the path of the bicyclist, and the bicyclist might make a left during that point, and that's what it is actually predicting. And there's a lot of math and neural nets that do this inside the vehicle, which obviously takes a ton of training, and that's why you see a ton of miles collected for training, and it needs to face these scenarios as well to be trained enough to deal with them as well. So yeah, that's basically what you're seeing here, how it reacted autonomously to a very, very human behavior, which we as humans would, we know how to deal with this. But this is how a self-driving vehicle is taught how to deal with that. Moving on, how do we even get this in the first place, right? So this includes the concept of mapping. So like humans, if we use Google Maps, what we do is we look at Google Maps and then we drive, and we kind of have a sort of base map location that we go to, right? But in self-driving vehicles, there is obviously the base map, but that's not sufficient. The self-driving vehicle needs to know the lanes. It needs to know scenarios when it comes to traffic and prior states of the map, as well as the point cloud data of the signs, road signs, as well as the traffic lights. It needs a lot more layering than a regular sort of self-driving vehicle. A regular sort of human-driven sort of vehicle. That's why you can see the base map, which is obviously something like a Google map, and then it needs the point cloud data, which is the geometric map that it layers on top of that, and then it layers a visual geometric map on top of that, which it renders. And then there's a semantic map, which includes all the lanes, all the pathways, all the traffic lights, everything like that. And then on top of that, there's the scenario and map priors that it uses to understand what's in its path, or what a certain scenario is, right? This is how, in general, there's a map, an area is mapped in multi-dimensions to make self-driving possible. Now, when it comes to what it takes to build a career in self-driving, even, or in general, right? How are these vehicles on a hardware standpoint, designed and deployed and stuff like that? I like to show this sort of a process. In general, it is no different from a lot of other processes. Of course, there's regulation, and there's a lot of things around standards you need to meet that needs to get met. But in general, there's the product requirements, which makes sense from a business side, fed in. Then there's a problem that's defined. Then there's a prototype. The prototype goes into sort of a test, a build, and then it goes into testing. And after the testing, you improve that, evaluate it, then research again what's bad. And it's a continuous cycle, and you have milestones coming out in the form of solutions. So this is basic a general hardware sort of engineering process that I'm showing over here. But the real question is also, where does it stop, right? So robotics, is it just self-driving? Or even self-driving, is it just in passenger vehicles, or where is this even going, right? when it comes to where is this going, here's an example of a very early prototype of, like, someone trying to automate a tractor, right? So there's like all these things in addition to its motion, right? It has to do probably some sort of like plowing and things like that, that needs to get automated. There's the main computer for the decision making, and then there's like a little prototype sort of sensor pod over there with a few cameras. Someone seems to have hacked a few CCTV cameras on there for perception. So farming will get automated. When this technology sort of evolves and advances over the years. What you can see over here is a company called Built, right? There's a typical construction site, but if you notice, there's no human inside those equipment, right? It's completely autonomous. They all work together. And imagine you can probably reach a state where this can operate with the same amount of efficiency under dim light or no light, as it will under like a fully lit sort of daylight kind of situation. So this brings in a lot of efficiency into businesses. Of course, it brings with it the question of, oh, what about the jobs of the people that are working in it and stuff like that? That's a very interesting question that there's a lot of debate going on. But I am here to talk about the technology, and this is actually where it's going. And you can see here where this is an autonomously driven sort of what do you call this, by the way? It's a shovel kind of thing. And you can see no driver inside it, and it's actually moving. And a few of my friends have started a company that makes these kinds of vehicles. This one is a startup that is based out of Africa, where they make autonomous airplanes, and they use these airplanes to deliver blood and vaccines to places which do not have proper connectivity. And this basically goes and drops the blood packet in the hospital that it needs to get delivered to, and that's how drones are being used in healthcare as well. Now your question is, how does this even land, right? Do you need a runway to land it? No, they were pretty innovative in this. Just like they launched it in a sort of catapult environment, they also designed a system that the plane can precisely sort of maneuver on top of, and it catches the aircraft. So you can see that it's being caught and lowered. So it doesn't even need a runway. So it can complete a mission, come back, and get another sort of sample. They've also made the batteries very, very sort of modular and replaceable. So it gets another sort of packet of blood or vaccine or whatever it is, and it's off to go immediately. So these are all like very, very interesting business problems or real world problems that are being solved with robotics. And of course, this talk is probably incomplete if I don't mention this is something you might have seen. You all might have seen. It's went pretty viral. These are robots from Boston Dynamics, and they made a pretty fun video of them dancing to a tune, and a lot of like such fun stuff. So yeah, in general, my message here is that self-driving and robotics is a very, very sort of exciting area that everyone should consider going into. And sort of this is the biggest problem that a lot of people are working on. And 2020 and 2021, I think, are the years where we have sort of understood that self-driving vehicles can be commercially viable as well. So up until now, probably, right after Google started it, I don't know, about 10 years ago, something like that, people were just, talking about it like vaporware, or it just won't go anywhere. Probably even if the technology is ripe, the solution might not be necessarily ripe because it won't make business sense, stuff like that. But what the pandemic has taught us, and also what 2020 in general, self-driving businesses have moved towards, is a clear sign that it pretty much checks all the boxes, right? We are capable of developing the technology if we if we work long enough at it and make relevant improvements, we are capable of making it commercially viable as well. So when there's all these criteria that are being proven, there is nothing that will like really stop this revolution from coming. So the only question is, if you on what side of it will you be? Will you actually be in the revolution making it happen, or will you watch from the sidelines, right? And that's why I'm really excited to rally around robotics and make a lot of people sort of excited about this. And that's what I kind of wanted to do in this talk as well. So like I mentioned, if you want to get in touch, I'm pretty active on LinkedIn. That's pretty much where I do all my sort of posting and stuff like that. I'm also available on Instagram, so feel free to follow me there. Stay in touch. I think with that, we'll open for the Q&A. I have gotten a few questions over here, which I'll just present, and then maybe we can go into those other questions. So during nighttime, let's say there are no street lights, what happens then? A case happened in Arizona where a Uber autonomous car accidentally hit a woman as the driver in it was not paying attention to the road, and the sensor judged her as a cyclist. So there are a bunch of things that went wrong over there. So a few things are established in fact, a few things are speculated. One of the things that's discussed in that case is that they lowered the tolerance of they lowered the margin of tolerance of their sensors, so that they don't get false positives when it comes to sensing. So because that threshold was lowered, the vehicle did not necessarily detect the pedestrian or the cyclists as a like real threat, and it never braked. And by the time the driver actually got involved and slammed the brake pedal, it was too late. So that was basically what happened over there. And I don't if there are no street lights, then the vehicle is people drive under no street light scenarios all the time, right? There are headlights on the vehicle. So that lack of street lights was not an issue over there. The issue was bad adjustment of the tuning that the self-driving system had. Going into Vyas's question, what kind of microcontrollers, DSPs, ECUs are used in the self-driving vehicles? How can one start with such development at a very, very low budget? These are a few disjoint questions here. So there are early development. Usually, I've seen people do early development with non-automotive grade hardware, and that's where you don't necessarily need a lot of you don't need automotive grade redundancy or automotive grade hardware in terms of like error handling and stuff like that. But in terms of microcontrollers, so there are basically two types of computation, right? There's the high performance compute, where you have the CPU and the GPUs and stuff like that are able to sort of pull the load when it comes to when it comes to the main perception stack. But then there are some things that can never fail at all, which are the high integrity requirements, like microcontrollers, ECUs. ECUs are basically like a certain variant of sort of microprocessors sort of packaged. That's basically that. And how can one start with such development at a very, very low budget? If you want to implement it in a self-driving vehicle that needs to be street legal and stuff like that, it's going to be a little hard. It's going to take time and energy to and money to actually develop that, because you need like automotive grade reliability on that. But when it comes to basic functionality implementation and testing out functionality, that's a different story. You can use some medium performing DSPs or ECUs or microcontrollers for that. Does Tesla and other companies use model predictive control? I can't speak about Tesla in specifically, but in general, yes, the industry does use this. In the autonomous airplane to deliver vaccine, wouldn't it be easier to make them in a way of drone so it will be easier to do vertical lifts? That's a really interesting question, actually. So, a good analogy of this is, why can't all airplanes that you travel in be helicopters, right? So each has its own strong points. For example, if you catapult a plane like that and launch a plane like that, you'll need far less battery, or far less energy to launch it, right? And when you do that, the size of your battery goes down. What happens when your size of your battery goes down is you can carry more payload, and deliver more stuff, or you can reduce the weight of the plane and probably increase the range that way. So when it comes to vertical takeoff and landing, that's a very interesting problem in itself. But in order to make this very sort of agile, cost effective, and enough for that specific purpose, uh, that's why they did it that way. What's the computational speed of a Tesla, and how does it manage to achieve it? This basically keeps changing. It keeps evolving. So there was, like, several variants of autopilot hardware, and there's a public presentation about, like, the most recent autopilot sort of hardware release that you can watch online. As far as, like, the specific numbers, I'm not aware of, like, the very specific numbers, and even if I was aware, I would refrain from like mentioning that. I think there's a decent amount of publicly available presentations that go deep into. One of those is the Tesla Autonomy Day presentation. So if you sort of uh, um, uh, search that on YouTube, you'll see, like, a really good insight into the latest sort of self-driving chip that is designed from the silicon itself. Because going with other sort of compute vendors doesn't make sense at that point, because they keep running into the walls when it comes to hardware capabilities and computational capabilities and stuff like that, which is why I believe Tesla started their own silicon and chip development process. Okay, what new tech should we hold on? What new tech would we expect from Cybertruck and Tesla Roadster? What new tech would be expect? Um, Again, the specs are pretty public. I mean, what I like about these two, or anything that Tesla does from a personal standpoint, is that they are all heavily functional vehicles which look pretty badass, right? Where it's not like the Cybertruck. I don't think the Cybertruck is, like, necessarily designed so that it can look badass at the cost of everything else. For example, the unibody sort of frame and the sort of base of the flatbed behind it, and why the grooves are present, so you can functionally use it to tether something down, or there's the power plugs at the back of the flatbed, and those are present so that you can sort of use that as a power outlet for other things that you want to do, like while camping or while loading some construction equipment and things like that. So I think the amount of attention Tesla has paid to user sort of needs, and functionally implemented that in their product, at the same time making it, like, manufacturable and look really good. I think that's the genius that those all the teams working together have brought to the table. Let's go to the next one. In the first slide, there was a 3-wheeled vehicle. Can you explain automation implemented in it and about that vehicle? I'm not sure which the 3-wheeled vehicle was. Yeah, I'm not sure which one specifically you're talking about. So if you can clarify that, that'll be great. Feel free to submit another question. Why does Tesla don't have a drowsiness detection feature yet? I'm not entirely sort of sure of that, but here's what I know, right? Like, and this is again publicly available information, which is Tesla steering wheels have pressure sensors on them, which basically require you to hold on to the steering wheel for the vehicle to know that there's a driver present and paying attention. And if you don't for a decent amount of time when it's on autopilot, it'll warn you. And in instances where you haven't necessarily regained control of the vehicle, there are some cases where the vehicle has pulled over to the side, turned its blinker on, and parked and stuff like that. But yeah, that is some form of a drowsiness detection feature. Now, when it comes to, if you're asking specifically why it's not doing what other car companies are doing, which is implement a camera, watch the driver, and sort of look at their eyes and make sure that they are not drowsy enough. I think that Tesla is playing the long game, where in the long term they are planning for no driver to be in the vehicle at all, right? So when that's the case, this problem is not present at all in that scenario. So now it's the question of getting to that stage quick enough and doing something that is just sufficient from now to getting to that stage. And I think what they have implemented is a manifestation of that sort of type of thinking. In the future, when we achieve full autonomy, can there be a chance that self-driven vehicles take the route which has more malls and offers going on just to increase sales? Are there any policies regarding this? Really interesting question, actually. I know for a fact that there are companies looking for looking to monetize based on advertisements. Now you have brought a so totally different sort of dimension to it, where the car actually takes a route and drives you by malls to make you crave shopping. Probably it might happen. As far as policies regarding this, I think it depends on the service that people buy, right? Like look at YouTube policies. There's nothing preventing YouTube from showing you an ad if they have discounted your offering in exchange for that ad being shown, or if they are providing it for free, right? So I think a lot of these self-driving sort of services will look a lot like digital products when it comes to general sort of advertisement, monetization, and stuff like that. Now that Tesla has entered the Indian market, how can one apply? Will the candidates project in this domain help them secure a job in Tesla? I'm not aware of. I'm not sure how to answer this question. It's again, I can't necessarily speak for the company, and I'm not part of that company now either. But what I can say is there might be like other opportunities that come up within Tesla in India that for sure will be displayed on their career space. So keep track of that, and make sure you apply. So will the candidates project in this domain help them secure a job in Tesla? Like in any sort of company, relevant experience in that area will definitely help. And a lot of people have sort of reached out to me asking for like resources and other things to actually get their foot into the self-driving world. So I have actually routed them to a few resources that they can read and stuff like that. But when it comes to moving from a certain industry to a certain different industry, let's say, I don't know, like semiconductor or something like that, into self-driving itself, will take a little bit of a learning curve in terms of like understanding what the self-driving world looks like, what the development culture is in that world. And if let me know if you all are interested in such resources and stuff like that. If there's like sufficient interest, then I'm happy to sort of make a course, an online course or something like that, that's very specifically targeted for such people who want to like make that transition, with enough information that will help them do that, and put it out there online. So yeah, let me know. Please feel free to like message me on LinkedIn if you are interested in such a thing, and I'll be motivated to make that available. Hydrogen based car was introduced in CES. Any thoughts on that? Hydrogen based car is a very polarizing kind of thing, because people like Elon Musk think that although it is a form of clean energy, it's not necessarily scalable, or it doesn't necessarily solve a lot of problems compared to a self-driving electric vehicle. And my stance on this is the following, right? So in order to transport hydrogen, you need to basically build the same physical transportation infrastructure, or pipelines and things like that, new pipelines and things like that, to distribute hydrogen. Imagine you have gas stations, right, and or petrol stations, and you want to transport gasoline or petrol to these stations. You still need tankers, you still best case would need pipelines to do that. But think of electric. What happens in electric is you have electricity being transported almost at the speed of light, or at the speed of electrons, right? Which basically reduces a lot of like infrastructure needed to get electricity from one point to the other, which gets rid of all that additional cost of infrastructure building from a business sense. But more so, electricity is also capable of being harnessed through solar, right? Which might also mean you don't need a line or an like a wire line connection to get that electricity. You can probably put a solar panel that is sufficiently efficient, and then serve that sort of station with that solar panel. And that's what a lot of supercharger stations are doing as well, in the US and around the world. So that's what Tesla is trying. So I think electric versus hydrogen, if I were to invest efforts in bringing something to life, I would definitely invest it in electric. I was talking about the vehicle in the first slide, which woman is there, but can you explain more about that vehicle and the automation implemented in it? It's, I mean, it is similar to other autonomous vehicles in general. There's lidars. I mean, that's what I can see. There's lidars. There's I think there's like radars in it. I'm definitely like sure there's cameras in it. So whatever I've explained until now, when it comes to like in general how self-driving vehicles work, I don't think that vehicle is necessarily different from that. The one key difference though is that you look at Waymo vehicles, which are those vans, right? Like the one that avoided the cyclist. That is an off-the-shelf, or like a market-made Chrysler Pacifica vehicle, and then there's a bunch of sensors and compute put on it, and that becomes a self-driving vehicle, right? Where there's a vehicle already made from another company, and this new company, which Waymo in that case, which is like a subsidiary of Alphabet, started with the Google self-driving car and stuff like that, that attaches additional self-driving technology to make it self-driving. Now, the other type of self-driving vehicles are ground-up self-driving, right? Like, for example, Teslas From day zero, they were not built with self-driving technology, but now they are built with full self-driving technology embedded in them, right? So anytime you buy a Tesla, it's impossible to buy a Tesla which is not capable of full self-driving. They just don't sell it. There's the Zoox vehicle that you saw, which was also built like ground up. The entire vehicle is designed and made for that application, and that's what's like super exciting about that. How will the self-driving car be able to detect potholes or speed bumps? Yeah, I mean, the vehicle has cameras and also sensors, like in form of like lidars in some cases, as well as radars that when appropriately placed, I believe will be able to detect these. But good question. Just a random thought, will it ever be possible to develop an EV that is powered by a tiny arc reactor, just like in Iron Man? Oh, nice. I like this ambition. I think probably, but you can do a lot of like things happen actually. If people invested sufficient resources into stuff, maybe they could make a nuclear reactor kind of car also available, right? Why isn't that? Because why isn't that there yet? Because of either it doesn't meet a business sense, or it doesn't meet a logistic sense. There's a lot of such, or it's not just not worth it from the point of safety, where it might be the safest vehicle ever, but that one time it might crash, it might destroy the whole world. You don't want to sort of be in such a vehicle. So yeah, there are such limitations from an overall standpoint, even if a certain technology might be possible. How do you see the future of robotics and self-driving cars, say in 20 to 30 years? A lot more than what it is right now, and there are ways that it will take that we will be interacting with robots and self-driving vehicles, and like in general all types of robots, in ways that we haven't imagined yet. Now, if you ask someone, let's say 20 or 30 years ago, if they would be able to access all of the world's information at their fingertips at the click, just a click of a button, people would have said, you're crazy about what you're thinking, along the lines of what you're thinking. But that is possible in the form of cell phones, high-speed internet. So there are all these abstract technologies that are coming up that I am very, very bullish about the robotics and self-driving space, that this will happen in the next 20 to 30 years, or if not, like much sooner. I think there was one more question around here. Is Carla Simulator good for autonomous driving research? I'm not entirely familiar with Carla Simulator. I don't know. But yeah, feel free to reach out offline and we can talk about that. I'll probably do some research on this. Any more questions here? Okay, there are actually a ton of questions and I have to go in a couple minutes, so I'll go through this really quick. How do you see the future of self-driving vehicles in India? I think the biggest thing is the infrastructure, and there has to be a certain bit of like innovation in infrastructure, where things are more sort of predictable across states and stuff like that. I think that is the biggest sort of impediment there. I don't think that connectivity is an impediment, because to be honest, I feel like the 5G or 4G LTE connection that India offers, people in India, is significantly better than most places in the world, and it is the cheapest data that you can ever get in the world. So I am very, very bullish about connectivity and such things in India. Maybe it can get a little more reliable, but in terms of connectivity infrastructure, I'm very, very bullish and very positive. What I'm sort of iffy about is the actual sort of uniformity of roads, uniformity of signs and everything like that across the country. But at the same time, this is a really interesting problem. If there's no infrastructure and you want to bring self-driving vehicles, figure out a way to make that infrastructure happen. That way you open up opportunity for all these self-driving vehicles to sort of make their way in, right? So I think this is a really good startup idea or a problem to sort of start thinking about. What will be the first thing one should start changing or replacing from? What will be the first thing one should start changing or replacing from current situation? I'm not entirely sure what that means. Some clarification will help. What kind of analysis goes into predicting the surface? Like how does a vehicle avoid the surface when which can potentially puncture a wheel? Again, it comes to like sensing that first and implementing, maybe high resolution cameras or some more precise sensing modalities into the vehicle will definitely make a difference. As far as like puncturing a wheel, there are, I think, other ways also to deal with that. Like you can rate your tires enough or rate your entire vehicle such that it can move with the punctured tire for a certain distance, let's say like 5 miles or something like that. Or you can make like a tire that doesn't necessarily puncture itself, things like that. What are all the areas where self-driving car manufacturers look for cutting the cost? There's a fair bit of things, right? Like if you can improve your sensing modalities so you can cut down the number of sensors, maintaining the same level of redundancy, then you've kind of cut the cost there. But in general, I think it is also around manufacturing efficiency, right? So there is this company called Arrival, which has like innovated a lot in factory and manufacturing sort of cost cuttings. You might want to take a look at that. They are doing some super cool stuff. It's called Arrival. How does self-driving car react after an accident? I want to know in terms of accident notification to emergency services, car damage, passenger safety, etc. Yes, I mean, it doesn't need to be self-driving. There are vehicles, I think, that already do this, where they call up an emergency services, deploy airbags. So this problem is like relatively solved. But then when it comes to how it, like if it loses its sensing or if it loses its actuation and stuff like that, how it will pull over, all those questions need to be addressed. How does it even retain enough capability to even pull over, right? Those questions sort of need to be addressed, which is an active sort of research topic as well. All right, so I think I've gotten through all those questions, and I'll hand it over to Arpan.
Sure, thank you very much, sir. Really am thankful to you. And the session was very much interactive, which means that a lot of people are after this self-driving vehicles, and I think you can do help all the students out there and the faculty members as well can work more in this direction. So I'm pretty sure that you wouldn't mind answering their questions, even if they come to you later on, after the session as well. And I'm sure that they are going to come to you.
Yeah, feel free to reach out to me on LinkedIn, send a message, follow me on Instagram and LinkedIn as well, and feel free to reach out to me anyhow. If I think there's like some resources that are sufficiently sufficiently answer your questions, then I'll route you to that resource. But if you're interested in sort of self-driving transition and stuff like that, let me know. Happy to make a course around it if there's sufficient need there.
That's very kind of you, sir. Okay, on behalf of IEEE Signal Processing Society, I would like to thank IEEE Section, IEEE Signal Processing Society Gujarat Section, Chair of IEEE SPSGS Committee members and volunteers for the successful conduction of the talk. I would like to thank the participants, without whom I don't think the event would have been this successful, and the interaction was very healthy, as I can see from the questions itself. And not but least, Saiman sir, yes, I extend my hearty gratefulness that you accepted our invitation. And to acknowledge our gratitude, I would like to present a memento on behalf of IEEE Signal Processing Society, sir. So I'll just like to. So here is a memento on behalf of IEEE SPS GS section, sir. Thank you very much for your talk. That was very helpful.
Thank you.
Thank you very much. Thank you.
All right. See you. Bye.
Okay. See you later. Thank you very much. So to all the participants, I have shared a link, which is the feedback link. From there, you'll be able to download the certificates as well, which I'm sharing with you once again. Please fill the feedback form link. And after filling the feedback form link, you will get the download link for the certificates. So please do the needful. Right? Thank you very much for attending the same. And I'm extremely sorry for the inconvenience caused for the WebEx platform. Right? Okay. Thank you.